let's get into the product what we can get from CH3Cl. Why would we make this CH3Cl? So from this we can have so many types of products. As you can see, if you just react in presence of dilute HCl or OH or an either a dilute acid or a dilute alcohol. Okay, so what would you get is you would get an acid and carboxylic acid from cyanide. So this is called a hydrolysis reaction. Okay, but if you just react this cyanide with concentrated acid or H2O2OH minus, you would get what you get is an amide, right? And if you just reduce it in presence of NaETOH or lithium aluminum hydride and nickel hydrogen, these are the reducing agents, then you would get, definitely you are going to get an amine. So this reaction, sodium ethanol, is known as Mendeus reaction. MENDIUS, Mendeus reaction. Okay, so you would get this type of amine. So let's look at the mechanism of these three reactions. So first things first, I'm discussing about this reaction first. Okay, how would you get amide in presence of H2O2OH minus and concentrated HCl as well? So first thing that happens is, first, when cyanide is there in presence of water, so water, the lone pair of oxygen would attack this carbon. Why? Because this carbon is a polar part. Because nitrogen is more electronegative, so nitrogen is dragging this electron towards itself, and this carbon is very much in positive state. Okay, so this is attacking the carbon center, and we would get this thing. So first we would get this OH2 plus, and after that what would happen is intermolecular acid-base reaction would happen. So what would happen is, you can see, we would get something like this. After this attacks, the minus charge would be there in the head of nitrogen. Okay, and there would be, and the oxygen would give us this product, and this hydrogen after that would get abstracted by this nitrogen minus. I'm showing you the mechanism. What would happen is, CH3 C triple bond N was there, right? So when H2O is reacting, this lone pair is attacking it, and nitrogen is getting N minus. So we would get CH3COHH and double bonded N minus, right? After that what happens is, this hydrogen is getting abstracted by this minus charge. So this is a base and this is an acid, because this is donating hydrogen, this is abstracting hydrogen. So we call it an intermolecular acid-base reaction. Okay, so it happens with the help of water. Okay, first what happens is, water is taking up the hydrogen and becoming H3O plus, and after that nitrogen is taking up the hydrogen from H3O plus to give us this product, CH3COH double bond NH. Okay, this is how we are getting this thing. So this is called an intermolecular acid-base reaction. Okay, so we are getting this as a product. So after that what happens is, this H2O2 and OH minus, you can see that here H2O2 and OH minus was there. So this H2O2 and OH minus together, this OH minus as a base is abstract this hydrogen to make this as a product. Okay, so now HOO minus is a very good, works as a very good base. Okay, so HOO minus is abstracting the hydrogen, and this bond is getting over here, and this bond is getting over nitrogen. So this is a resonating structure. So we would get this thing. So after that, this minus charge would abstract this hydrogen from the water. Okay, so that we would get the amide. Okay, similarly, the same reaction in presence of HCl, what would happen is, first the reaction and the formation of this. Okay, first this thing is the same for the next reaction as well. So after that what happens is, this lone pair pushes back and this bond gets over this nitrogen. So we are having the same reaction here. After that, this minus takes up the hydrogen from the HCl. Okay, previously it was water, now I have an acid, so I can get this hydrogen. Okay, so nitrogen is getting this hydrogen. After that what's happening is, after that we can conclude to this product. Okay, so this is how this reaction happens, this reaction occurs. Now Now the last thing is, we have discussed about all the things. Wait for a second. Okay. Now we have discussed about the mechanism of this reaction, right? Now we are going to discuss about the mechanism of this reaction, how carboxylic acid is being formed. So as you can see, first water attacks the carbon similar way in presence of dilute acid. So we get this thing like the similar way, intermolecular acid base. Okay, this is the same for all the things. After that we get this thing similarly like the previous one, the amide would form. Okay, the same mechanism. But after that, in case of this, as this was dilute acid, so there was a huge amount of water present in this. So water would act as a nucleophile, and it would attack this carbon. This bond would break, and it would come back, and this bond would get broken. So we would get this acid, carboxylic acid. Okay. Now the last reaction here, I have nothing to show about this because this is a normal reduction reaction. So as you know, lithium aluminum hydride, sodium borohydride, these are the very good reducing agents. So they just give us H minus, okay, hydride ion. So this just provides hydride ion to reduce these things. Okay. Okay. Now, if we are done with this, now the next part is substitution by isocyanide groups. So what are the isocyanide group? The NC, right? We have learned about substitution by CN. Now we are going to learn about the substitution by isocyanide. So if you just put some AgCN instead of KCN, you would get this isocyanide. So how is this happening? So in the previous one, KCN was an ionic reagent, right? K plus Cn minus. But in this case, AgCN is not a proper ionic species, as Ag being a transition metal, it has a high Z effective. Z effective means the effective nuclear charge. So for that reason, resulting a covalency in AgCN. So as you know from the Fagen's rule, the cations having more effective nuclear charge form some covalency in the compound. So here AgCN is like this. In the previous reaction, KCN was there in the form of K plus Cn minus. But in this form, in KgCN, Ag is not in the state of Ag plus Cn minus because of this covalency. Where is it coming from? Because Ag is a transition metal having greater Z effective. Why it has greater Z effective? Because of the deconstruction or the F contraction. You have learned about it. Okay. So here deconstruction is the main thing. So it is like this. So after that, what happens is this bond breaks here, and the nitrogen lone pair would react would attack the R group. So what would happen is this X would get out as a leaving group. So we would get isocyanide. So nitrogen is the atom from which it is getting attached. Similarly, for nitration, if you use KNO2, you would get ONO because KNO2 resides like this, K plus ONO minus. So you would get ONO as a product. But if you use AgNO2, so AgNO2 is like this. So if you use AgNO2, then the product is going to be, as this bond breaks and comes over oxygen, and this lone pair of nitrogen attacks the R. Similarly, okay, this is the same mechanism and gives us RNO2. So here nitrogen is the atom with which it is getting attached. But if you use KNO2, the attaching atom is O, oxygen. So this is RONO, and this is RNO2. So this resonance structure, this is the resonance structure, as you know. So this is the case. Okay, so that's all for today. In the next class, we will discuss about the substitution and the elimination reactions, like what are the SN1, what are the mechanism of SN1, SN2, and what are the mechanism of E1, E2. So we have already learned about them, the SN1, SN2, but still I'm going to discuss about them in details in the next video. Okay. So stay tuned and watch the videos and try to read these things clearly at home. Okay.